Dear colleagues, good evening to all of you. Thank you very much for being with us. And thank you for the organizer, Jim Calvin, Susana Nunez, and Marie-Laure Boulot. You're making signs to me or to somebody else? Oh, to somebody else. I don't think that saying that one is honored to introduce the speaker at any meeting is more true than it is for me today to welcome Claude Nicollier, whom I've met many years ago and about whom I would like to share a few words, very brief, because what is interesting really will come in a few minutes. But I would like to tell you that Claude is a professor of space technologies at EPFL. I also would like to tell you that he has been a very busy young man. He did his undergraduate at the University of Lausanne in physics. Then he moved to graduate school at the University of Geneva to study astrophysics in a very prestigious department where the first extrasolar planets have been identified. I told you he was very busy. In the meantime, he became a jet fighter pilot and, of course, an airline pilot and a test pilot. Then when eventually he decided to grow up, he moved to the European Space Agency and as such became part of some of the most prestigious research and space programs at the NASA, at the American Space Agency. Claude has actually been on 4 different space shuttle missions from Atlantis to, what was the second one? Discovery, Columbia, and Discovery. And you know Columbia was one of the 2 tragic losses at NASA. With Challenger, the 2 crew were lost. So adventure in space has all its meaning. Claude has actually spent more than 1,000 hours in space, of which 8 as EVA. You may know what EVA means. It means extravehicular activity. It's not very poetic, but he was one of a very short club of men and women that actually were hanging out there, out of the vehicle, linked only by an umbilical cord to the space shuttle. I know that we have some psychiatrists in the room, so they will make their image out of that. He has received many awards. He has received the Robert Collier Trophy, which is the highest distinction of the United States Aeronautical Society. He has received the Silver Medal from the French Air and Space Agency. He has received the Yuri Gagarin Gold Medal and the Albert Einstein Medal from the Einstein Society. Now, despite this extraordinary career and prestigious achievements, every one of you that will spend some time with him will take home the message that one can be such an extraordinary individual and at the same time a gentleman, a generous and an extremely kind and humble person. I really think, Claude, that if there were more people like you, or perhaps the space would be crowded, but the Earth would be a much better place. Thank you for being on us, and please join us today.
Well, thank you very much, Stefan, for your very kind introduction. And good evening, students, teachers, staff members of KAUST, families, colleagues. It's a great pleasure for me to be here. Since only about 23 hours, I landed a little after 8 o'clock yesterday, coming from Germany, or Switzerland via Germany, and I will leave already tomorrow afternoon, and it's too short a time, but it allowed me still to discover a wonderful institution, the KAUST, a great campus, and great promises for the future. So I'm very, very pleased and very thankful to KAUST, to Stefan Katsikas, to Marie-Laure Boulot, who organized all of the logistic aspects of my trip here, for this invitation to give this keynote address tonight. I also had the opportunity to meet various students today, physics students, and also a lot of small kids in a large room this morning where I tried to share my impressions of space travel. In fact, I had a short illustrated presentation called Space for Kids. And it's a presentation that I like because finally I find myself like a kid. Space is a wonderful environment, and it's absolutely ideal for kids and for adults who still have remained kids. It's really, for me, a great pleasure to be here and to share some of my space experience with you. In fact, I would like to have less light here, because the less light there is around here, the better it is, because space is pretty dark, and the darker it is in the room, the better the slides will show themselves. I gave the title Lessons from Space Exploration. We have learned a lot after a little more than 50 years of human space exploration. And through my own experience, but also the experience of others, of my colleagues, I would like to try to forward to you these lessons from space exploration. As you know, the first human to go into space in this climate of Cold War between United States and Soviet Union was Yuri Gagarin on the 12th of April 1961, a very courageous man. This was the time we didn't really know whether a human being would survive the space environment, mainly the absence of gravity, the weightlessness. And he was sent to one orbit around the Earth in 108 minutes. And he survived, obviously. Unfortunately, he died a few years later in an aircraft accident, but his first space flight was a success. It was totally irritating for the United States, obviously, but it was a big success for humanity. The proof that we can have people in space and they can survive the space environment and, as you will see later, not only survive but be productive in space. Yuri Gagarin, extremely respected person, and there's always in the International Space Station a picture of Yuri Gagarin, very respected. And the night from the 12th to the 13th of April every year, at the NASA Johnson Space Center in Houston and at Star City in Moscow is a crazy night. It's Yuri's night. We call it Yuri's night. And I can tell you that all astronauts and cosmonauts celebrate this remarkable accomplishment of Yuri Gagarin. Now, you know the American response after these first successes of Soviet Union in the early 60s in space. The first woman in space was also from Soviet Union, Valentina Tereshkova. The first spacewalk was made by a Soviet cosmonaut. But the Americans had to respond, and they responded in a magnificent manner with the Apollo program. It still seems incredible what was accomplished in the 60s until the first landing on the moon in the summer of 1969, Apollo 11. It seems so incredible still that many people believe it didn't happen, but please never believe the ones who pretend it didn't happen. It did happen, but it was an unbelievable accomplishment, following the words of Kennedy, President Kennedy, only 2 weeks after the flight of Gagarin. He said, "We are going to go to the moon, not because it is easy, but because it is hard." And the fact that it was so hard really created a focus of energies and talents in the United States that led to such missions. This is Apollo 16. The mission before the last. The last one was Apollo 17 in December 72. And in April 72 we had Apollo 16. And this was taken by John Young, the commander of Apollo 16. This is Charlie Duke. And at that time, they were using a small jeep that was allowing a larger area of exploration around the landing point of the lunar module. Apollo 16, John Young, Charlie Duke, unbelievable environment, totally dry, obviously, no atmosphere, so they had to wear a spacesuit, obviously, on the moon. Absolutely remarkable accomplishment. This is the way they saw the Earth, the Apollo astronauts, and that's really impressive. If you can imagine yourself, you are in a spaceship about 300,000 to 400,000 kilometers away from the Earth, and you see our home planet this way, a little ball with the dominant colors of blue and white, blue for the oceans and white for the clouds. This is really beautiful, and we are here. And in the middle you have India, the Indian Ocean below, beautiful. nearly incredible, but it happened. And some people, not too many, saw the Earth like you see it here. Now, all of the human flights after the end of the Apollo program, which was Apollo 17 in December 72, were in low Earth orbit. You see here, LEO is not for lion, it's for low Earth orbit, which means a few hundred kilometers above the Earth's surface. And all of the shuttle flights were on low Earth orbit. The Soyuz, the Russian Soyuz, goes to low Earth orbit. The International Space Station, I will talk about this a little more in a few minutes, is also on low Earth orbit. So nobody has gone beyond low Earth orbit except the Apollo astronauts on these missions to the moon in the 60s. But these are the characteristics of the low Earth orbit: a completely black sky because you are outside the atmosphere. The atmosphere is very thin and very close to the surface of the Earth. And it's really a beautiful view of the Earth. And of course you need to reach a pretty high velocity of about 28,000 kilometers an hour to stay on low Earth orbit. If you, during the ascent or the end of the ascent, cannot reach that velocity, you'll fall back down pretty rapidly. If you are too fast, not a big problem, you come on an elliptical orbit. But for each altitude you have a certain velocity which is quite high when you are close to the Earth and goes down as the orbit is higher above the Earth's surface. And of course, in order to reach low Earth orbit or any place in orbit, you need a powerful machine, a rocket, or the space shuttle that was developed at the end of the Apollo program by the Americans as a reusable spacecraft to reach low Earth orbit. Reusable, and this made it a very challenging program. The fact that this winged vehicle was flying several times, it had to have a reusable thermal protection system because the heat of reentry is very, very high. And that was a very challenging program. I would say a successful program in the sense that we had, within the 30 years of the shuttle program from 1981, first flight, to 2011, the last flight, 135 flights. Unfortunately, 2 major accidents, Challenger in '86 and Columbia in 2003. So finally, when we look back, it was a successful program in the sense that we accomplished a lot with the space shuttle. A lot of astronauts went into space using the space shuttle, but it was finally quite expensive and it was rather dangerous. And you have 3 hydrogen engines sucking the content of this big tank containing liquid oxygen, liquid hydrogen, 700 tons to reach orbit in 8.5 minutes. But the thrust is not enough with these 3 rockets engines. You need extra boosters, solid rocket boosters, that are burnt off after 2 minutes and fall back in the ocean, are recovered, or were recovered, I have to use the past, for future flights. So this is a space shuttle with a huge payload bay, could take up to 20 tons to low Earth orbit, and a cabin like an airliner cabin for up to 7 people. Now I have a small video clip that will show you the first part of the ascent of the space shuttle to orbit, the first 2 minutes until separation of the 2 boosters. So pay attention. It's going to be relatively noisy like it is in this initial part of the flight. But this is the way a mission of the space shuttle starts, from main engine ignition until separation of the boosters. 7 people up there in the cabin. Shaking in the cabin, you see. Roll maneuver to take the proper plane of the orbit. That's from a small camera on the external tank looking down. This is the coast of the Atlantic Ocean. And bang, booster separation, and they fall down in the ocean. You see, this is about 2 minutes after liftoff, and the sky is completely black already. You're on your way to orbit, and you continue your ascent to orbit with the shuttle only, with a big tank, and using the 3 hydrogen engines only. And then here you are, you're on orbit. And there's a huge contrast between the dynamics and the noise and the shaking. Not too much light in the room, please. Less light. And the quiet phase on orbit, where you have absolutely no noise. You don't have any more engines to be used for propulsion. You only use small engines for attitude control. And it's a beautiful sight. You see the black sky, the sun, the Earth upside down. This is the so-called terminator. It's the limit day-night on the surface of the Earth. Here it's day, here it's night on the Earth. And on the average, every 45 minutes you come over the terminator with the space shuttle. Really an amazing environment, visual environment. Nice picture of the space shuttle taken from a small satellite deployed on flight number 7 of the shuttle in 1984. The satellite was deployed from the payload bay and the shuttle moved away from it. So you have to imagine that the velocity vector of the space shuttle is inside the screen, 8 kilometers per second or 28,000 kilometers an hour, and the satellite is just following the shuttle, looking at the shuttle with an angle of attack of 90 degrees. Of course, there's no atmosphere, but this is what it looks like. Now, once, not a small satellite was deployed from the payload bay, but a human being. This is Bruce Mccandless, an American astronaut, who was spacewalking, but he had a little propulsion system, personal propulsion system in the payload bay. So he took it and using rotation and translation hand controllers, he moved away from the shuttle about 200 or 300 meters. And he was not tethered. He did not have a safety tether between him and the spaceship. So he was just flying free at 28,000 kilometers an hour. Any volunteers? If you once are given the opportunity to do this, you really need to say yes. This is an unbelievable experience. And very few had this opportunity. Bruce Mccandless did the first test flight, and there were a few other flights when NASA used it, but after a while they decided that, no, this is too iffy. So they decided that all the spacewalks in the future were going to be done with a safety tether. Bruce Mccandless, what a fortunate man. At the end of the mission, there's re-entry in the atmosphere. I was a flight engineer on my second flight in 1993, and I was sitting between the commander and the pilot. And this is a night re-entry of the space shuttle view in the cockpit. And you see the instrument panel, and through the windows, although this was a night re-entry, it's bright because of the very high temperature outside, typically of the order of 1,000 degrees. You come down to the atmosphere pretty much like a meteorite. And if you see a meteorite from the Earth, you see a lot of flames and sparks. And seen from outside, the shuttle looks the same. And it's very bright outside and very hot. And one of the big challenges of the shuttle design was really to protect the crew and the whole equipment on board against the heat of re-entry. And very successfully it was done. And it ended up with a landing, manual landing by the commander on a runway at Kennedy Space Center, Florida, which is also the liftoff point. You see the launch pad here. And after landing, the content of the payload bay is exchanged. Quite a lot of maintenance is needed, typically for a few months. And then there was another launch from the launch pad, which you see here. ISS is for International Space Station. The shuttle was used for the last 12 years of its operation from 1999 until 2011, was used to assemble this big complex of modules in space with a Russian segment, a US segment, a Japanese module, a European module. So there are, I don't use the past, but the present, there are 16 countries involved in this International Space Station program. Most of the elements were brought by the space shuttle, which you see here, docked to the International Space Station. Some Russian elements were brought by Russian rockets, Proton rockets. But it was really a big challenge to have these 16 nations cooperate in assembling this huge complex in the space environment, about 350 kilometers altitude. And it's large, pretty much like a football field. You see here the solar arrays, and the total size of the station is pretty much like a football field, more than 100 meters inside. Quite an accomplishment. And now that the station is completely assembled, and numerous problems that were encountered during the assembly and the early phase of operation are pretty much resolved, and it can really be used as a laboratory in space, normally by 6 people on board who do scientific experiments, Earth viewing, experiments in astronomy and material science using the microgravity conditions. Nice picture of one of the, well, this is the shuttle flights before the last. Last one was STS-135 in July 2011. This was the one before. And this beautiful view of the shuttle attached to the International Space Station, picture taken from the station. And you see in the background the Earth horizon, you see the stars in the background, and the cities, they have moved a little bit during the maybe 10-second exposure. Beautiful view. This is gives you a real visual impression of the beauty of space on low Earth orbit. The payload bay is illuminated by floodlights. That's a payload that has been grappled by the robot arm of the station. This is the alpha magnetic spectrometer built partly in Switzerland in order to record cosmic particles from the International Space Station during several years. So typically the shuttle was going up, docking with the station, then the content of the payload bay was extracted with a robot arm and installed on the station. Nice picture of astronauts on board the station. I mentioned 6 people on the station. Yes, 6 that were remaining in the station, but when the shuttle was visiting the station, which happened quite often, there were 7 people on board the shuttle, plus 6 on board the station, 6 plus 7, 13. And here you have 13 men and women, astronauts and cosmonauts, in star form to indicate the absence of gravity in the International Space Station. Quite a nice view. Mainly American and Russian astronauts and cosmonauts, but you have one American woman, another American woman, you have a Japanese woman, Japanese man with head down. So astronauts from these various cooperating countries are working together and spending normally 6 months in the station before returning to Earth. My personal experience, I studied physics in Lausanne, Switzerland, and astrophysics. I spent quite a lot of time in an observing station doing work at the telescope to record data on stars. And the data was being analyzed in Geneva, at the Geneva Observatory. We had a nice observing station near Zermatt, Switzerland, a beautiful landscape with the Matterhorn here. And that was the telescope and the photometer we used to do this work. I spent a lot of time piloting airplanes also. I was a military pilot, part-time military pilot, and spent 22 years flying this fighter bomber, Hawker Hunter. It brought a lot of pleasure for me, but it's obviously work that requires discipline also. So it was a good training for spaceflight. Spaceflight is fun, but it's discipline at the same time. It's work and discipline. We had interesting exercises where we took off from highways, but there were bridges, so we had to be careful with the bridges because you cannot lift the nose of the airplane before you go under the bridge. That's pretty obvious, but you had to be careful. Yeah? That was really a lot of fun, but at the same time a rigorous exercise in precision and discipline. I was sent to Houston after being selected in the first group of ESA astronauts in 1978, sent to Houston in 1980. This is Houston, downtown. The Space Center is about 30 kilometers south of here. We did not train in this part, but this is a big oil city, Houston. A lot of banks and oil companies are based over there in Houston. But we didn't spend too much time in these high-rise buildings, more time in the Shuttle mission simulator. The shuttle is a very complex machine, and in order to understand it and operate it safely and efficiently during all phases, the ascent into space, the on-orbit phase, the reentry, approach and landing, you really need a lot of training. Pretty much like the cockpit of an airliner with the seat of the commander left, the co-pilot right, and this is the seat of the flight engineer, position that I occupied on one of my 4 missions. Spacewalking training, EVA, as was mentioned by Stefan before, spacewalking training in the water, a large tank in the vicinity of the training center, and there were models of the International Space Station, of the airlock of the Space Shuttle, the cargo bay, and the Hubble Space Telescope in preparation for Hubble missions. A lot of flying also. Flying is a big thing at NASA. All astronauts, whether they were originally military pilots or civilian pilots or engineers or medical doctors or scientists, we all learned to fly the T-38. And it was used for travel and for flight training. We did not use Delta Airlines or Northwest Airlines. We flew T-38s. When we had to go to Denver, to San Francisco, to Los Angeles, to Orlando, T-38. A lot of fun. It's fast. It's much more flexible than being a passenger on an airliner, and it was training at the same time as fast travel. But there was no room in the cockpit for the toothbrush or the pyjama, so we had to put this in a luggage pod here. I miss this now. I left the European Space Agency as an astronaut now 6 years ago, and I don't have that privilege anymore. Now I have to fly airliners. You know. T-38, that was a lot of fun. But, again, at the same time, discipline. Flying such an airplane is fun, but discipline. First flight, space flight, was in the summer of '92, STS-46, 46th shuttle mission. And that's a crew, 7 people, Lawrence Schreiber, the commander, Marsha Ivins, we had a woman American astronaut on board, long hair, and you see how the long hair behave in weightlessness, in absence of gravity. The first Italian astronaut, Franco Malerba. This was a science-type mission. With partial success. We had success in some part of it, and I would say half success in other part of this mission. This picture was taken during this flight, indicating clearly the absence of gravity on board the spaceship. This is the cabin of Atlantis. This is on Atlantis, Shuttle Atlantis. You see the front instrument panel, the seat of the commander, and during the on-orbit phase, of course, we don't use normally these seats, commander and co-pilot. We just use the whole volume. And here 2 of my colleagues, I don't know who they are observing the Earth through the front window. But you see the complexity of the structure of the cockpit of the space shuttle. There were switches and instruments everywhere, on the front canopy, on the sides, on the ceiling, not too many on the floor, but it's a very complex machine. And you see that all of the switches were guarded with metal loops, because if you were in this position, you could easily change the position of the switch with your feet. In order to avoid that, all of the switches were guarded. Food. Everyone is interested how we eat in space. We don't eat from tubes like was the case in the early space program, but we took on board the shuttle the food in dehydrated form and dried form, so that we did not need a refrigeration to keep it for 10 days or 2 weeks in space. And these are scrambled eggs that have been rehydrated. We use water produced by the fuel cells of the shuttle. About 100 liters of water was produced every day. We use part of that water to rehydrate the food. The scrambled eggs, they had, once rehydrated, they had the texture, the taste of real scrambled eggs, and it was okay. You don't go there for the quality of the food. It's not gastronomy, but it was perfectly fine. And what is interesting is you see all these little blue areas here. This is Velcro. You cannot use a table like here on Earth. If I want to leave this laser resting, I put it here and it stays there, but in space you can't do that. So we have Velcro everywhere. You have Velcro on the food containers, you have Velcro on the Hasselblad cameras here, and all these little blue pads are Velcro areas where you can attach something. You can even attach people with Velcro if you want to, although normally we don't do that. But all these little blue pads are the equivalent of tables here on the surface of the Earth. Velcro. Without Velcro, no human space program. 2 out of my 4 flights in the 90s had as an objective to visit and do repair work on the Hubble Space Telescope, a really beautiful program and very remarkable program of investigation of celestial objects and measurements and picture taking of celestial objects. It's obviously an ideal position for a telescope, because all the telescopes on the surface of the Earth, they suffer from the atmosphere in between them and the object that you study. But Hubble has a perfect view of all celestial objects. Obviously, there is a price to pay for a telescope in space in terms of dollars or euros, and also in terms of complexity of the missions. needed to maintain the telescope in good conditions over several decades. The planned duration of life of Hubble in space was 20 years. It was launched in 1990. It is still alive and will still be for several years, but it was planned to visit it every 3 to 4 years to do maintenance work or repair work or improvements. Exchanging a scientific instrument in the focal area of the telescope was done several times. Now, to train for this servicing mission that were obviously done by rendezvousing with the telescope, grappling it with a robot arm, installing it in the payload bay, and then doing spacewalks, one spacewalk per day. When I say a day, it's a period of 24 hours in the flight plan. And we had to train for these in the water in order to simulate weightlessness conditions. And here we are training for this first servicing mission of Hubble. That was my second flight, planned for end of '93, in the water. I already presented that training facility before, but now you see the inside of this training facility. You have a very precise model of the Hubble Space Telescope, including doors which we could open, like on the real telescope. And we could get inside the telescope where we had very, very high fidelity models of the scientific instruments. All of the circuit breakers and cables were exactly like on the telescope. And the idea was to have such a high fidelity that when we were going into space, we are going to have the impression that we have seen this many, many times, just in the water. And in space you have no bubbles, no divers, but it was going to be exactly the same thing. Now we trained for a year between the summer of, or the fall of '92 until the fall of '93. And 3 days before liftoff, we took these little T-38 airplanes, went to Kennedy Space Center, spent the last 3 nights there. And at 2 o'clock in the morning, on the 2nd of December 1993, a little bus took us to the launch pad in the middle of the night. And I remember very clearly when we opened the door of that little bus, that's what we saw, our spaceship ready to go. And that was a very impressive moment. And they told us, go and fix Hubble now. And there was a pretty big problem with the telescope, which had a flawed primary mirror, which didn't have exactly the right shape. So the pictures on the focus of the telescope didn't have the expected accuracy. And we had to install an optical corrector. We had to change the solar arrays and do another repair work on Hubble. And we had trained in simulators and in the water. And that day we had to go and do it for real. Very impressive. In the middle of the night. And that was about 2.5 hours before liftoff. And at the liftoff, 4:26 in the morning, pretty early. A relatively short flight to orbit, which was only 8.5 minutes. And then we launched with such condition that we took an orbit which was inside the plane of the orbit of the target, so that our rendezvous problem was a 2-dimensional problem only. And we inserted the shuttle behind and below the telescope. Below means we go faster. That's the third law of Kepler. So we're going to catch up with the Hubble, and then we had to raise the apogee of our orbit in order to complete the rendezvous in about 2 days. And we found the telescope, not by chance. It was a very precise set of maneuvers to get to meet with it, grabbed it with a robot arm, installed it in the payload bay, and here it is. We are 600 kilometers above Australia on the 5th spacewalk of our mission, with one of my colleagues, Story Musgrave, at the end of the robot arm with his tools. And this is Jeff Hoffman, my colleague, and we are above Australia working on Hubble. We had exchanged the solar rays of the telescope. They had not been deployed yet. This is Australia here, Adelaide, south of Australia. This is Antarctica here. Really, really special work environment. Beautiful working space. Very special work, colleagues and friends. This mission had high stakes, really. NASA made it clear to us that we had to have success. They had launched a telescope with a flawed primary mirror, which was embarrassing for them. And they could not take the embarrassment of a failed first servicing mission. And we had total success. You see the new solar arrays are deployed. The telescope is still attached to us in the payload bay. We're going to release it to the free orbits, and we had really a good time. It was a hard mission, but with a huge satisfaction at the end because of the success we achieved. And there were very talented people that I had the privilege to be with. This was Story Musgrave, the most experienced NASA astronaut at that time. He was my hero. I took his haircuts even. I was so impressed by Story Musgrave. Dick Cavey, the commander, Jeff Hoffman, Ken Bowersox, Tom Akers, Katie Thornton, and myself, responsible for taking the picture. I still have my arm forward. Very special environment and very deep satisfaction when you have success on the mission, especially a mission like this one. I had the privilege of another visit to Hubble 6 years later. This was December 1999. This time we had a problem with the capability of the telescope to maintain precisely its attitude in space, not altitude, but attitude or orientation. We had lost gyroscopes, we had a computer problem, we had a pointing camera problem. We had to exchange all these components. And here we go, find Hubble again, following the same strategy for the rendezvous, installed it in the payload bay, and here we are, after opening the doors of the telescope in the instrument parts, pretty much like you saw in the water before. We exchanged the 6 gyroscopes of the telescope. On the second spacewalk, I'm here with Mike Fowle, my colleague, exchanging the main computer of Hubble, pretty much like brain surgery on a Hubble. We had to disconnect all the power lines and data lines, put them aside, exchange the computer, and then reconnect all the power and data lines. In avionic bay number 1, we had trained all of this in the water, and I was really impressed with how well trained we had been. I had the feeling this is another session in the water without the bubbles and the divers. But everything we had a knowledge of very precise, including all of the location of the handrails. The yellow handrails had to be used to move around the telescope, and the geometry was exactly the same as we had experienced many times in the water. And you see my safety tether, unlike Bruce Mccandless, I had a safety tether. I'm just holding myself at the edge of the door. My feet don't rest on anything. So if I push myself, which I avoided to do, then you become useless satellite of the Earth. Although if you have the safety tether, you can come back to the spaceship. But you need to be careful. Spacewalking is fun, but at the same time it's work and it's hard. I mean, you have all these elements that are combined. This end of this spacewalk, I took some pictures with a Nikon camera, and you see the open toolbox with power tools. We use mainly power tools, which are very precise tools, which give us certain torque. We can select a certain number of turns, and it will stop turning at a certain torque value. Computer-controlled, microprocessor-controlled power tool. And like astronauts and all instruments, each of the tools was attached with a safety tether, so we avoided to lose astronauts and instrument and tools. Fun. We are going to release the telescope after completing all the repair work, and this is a nice picture showing just before sunset. The sun is hidden by the telescope. It's about here, close to the Earth horizon, so you have a thin crescent of the Earth, and the sun illuminates the solar rays, so we had like huge gold foils with a completely dark background and a crescent of the Earth becoming thinner and thinner behind it. Really beautiful view. Hubble delivers every week a lot of very interesting picture on the universe. It's still properly functioning. We had the last servicing mission, which I was not part of, in 2009. It's working perfectly still and delivers pictures like this one, which is really magnificent. This is within our galaxy, a cloud of gas and dust with very hot stars that produce a so-called stellar wind, like the solar wind, a particle wind. And this wind has created kind of a big bubble in that cloud of gas and dust, except that some areas are resisting this erosion due to the flux of particles from the hot stars. And these are regions of increased density in this cloud of dust and gas. And these are future stars. This is the way stars are formed. accretion of matter inside clouds of interstellar gas and dust. And you have some objects that are extragalactic. You see here, this is a galaxy outside ours, this is another one, this is another one, another one, this is a galaxy, galaxy, galaxy. So it's interesting because this object is relatively close to us, typically a few hundred light years away, but you have a lot of objects on this picture that are very, very, very far away, typically millions or tens of millions, 100 millions of light years away, sometimes billions of light years away. Pretty impressive result. Now this is the deepest picture taken by Hubble. It's called the Hubble Ultra Deep Field. This was an area of the sky where there was nothing, a very small area, about 2 arc minutes by 2 arc minutes. 2 arc minutes is 1/15th of the diameter of the full moon, so you can imagine how small this little window is. The telescope was pointed to that empty window and left to collect the photons for 10 days. And this is a picture that was obtained. Unbelievable. The amount of galaxies that are visible on this picture is in the hundreds. And each of these objects here is a galaxy, except a few that are stars inside our galaxy. This is a star, this is a star, this is a star. So there are a few objects that are stars in the foreground. All the other objects are very far away galaxies, including galaxies that are as distant as about 10 billion light years away. Very impressive result, and showing the extreme richness in galaxies of the universe, and also a glimpse in the past of the universe, because the objects that are very far away, you see them as they were a long time in the past. This is a view of the Earth. I have a few pictures showing the Earth. None of my mission had as an objective to observe the Earth, but this is, of course, a background that you have, and when you have a free time, you don't read a book or look at the DVD. You're at the window, obviously, looking at the Earth. And in the International Space Station, you have a special room which is called the cupola, which has a lot of large windows, allowing the crew to have a very privileged view of the Earth. Himalaya, all of Himalaya. We are pretty much over China or north of Myanmar. Look to the west towards Pakistan, the high plateau of Tibet, northern India, Nepal, Bhutan, all of Himalaya in one glimpse. Hey, I found this picture of Jeddah. It's not a very high resolution picture, but this is where we are. Here, this is of course the Red Sea. We look to the east, and Jeddah is here, Mecca, pretty close. And this is Mecca, a pretty high resolution picture that I found on the on the NASA website of Jeddah, of Mecca. For the ones of you, and I'm sure all of you know Mecca because it's so close and so significant. This is it, Mecca seen from space. And this is not one picture, but this is a collection of night pictures of the Earth that has been assembled together to give you a view of our planet at night, and especially this part of the world. You have a good part of Europe, including Switzerland, which is not very bright because there are no big cities, but northern Italy has a lot of big cities, Milano, Torino. Interesting to see Egypt also, where you have light, you have people. And of course in Egypt, most people, they are in the Nile Delta. This is Cairo here, and along the flat plain of the Nile. And we are here in Riyadh, and the Persian Gulf, the Indian Ocean, Black Sea, Caspian Sea. Really interesting. Interesting from a human geography point of view. Once again, where you have light, you have people, and you see where people are. This is Riyadh by night. It's relatively low resolution, that's why I made it relatively small, but this is Riyadh by night. And I have 2 short video clips which will illustrate the dynamics of going around the Earth. This is going to be accelerated. We're going to fly over Africa with a thunderstorm under us, then we'll come over Egypt, and you know already what to expect at night, until sunrise around the Caspian Sea. Once again, this is accelerated. It's about 10 times faster than the real motion. This is taken from the International Space Station not too long ago. It was taken last year. Here we go. You see the thunderstorm here, the lightning, the Earth horizon. You see the stars rising in the east, and we are approaching Egypt here. And you know what to expect. This is the Nile Delta. This is the floodplain of the Nile. Israel here. We have Jeddah here, but fast. You see, this was the Big Dipper here, rising, turning around the North Star. And this is the Caspian Sea here. And you start to see northern lights here, green northern lights, the zodiacal light here before sunrise, and then in a few seconds you have sunrise. Bang, sunrise. But again, we go pretty fast, but not as fast as it. This is about 10 times accelerated. And now I have another short sequence over the Indian Ocean. You'll see the landscape covered by cloud, illuminated by the full moon. And you see a lot of southern lights. Southern lights or northern light, this is the same thing. It's basically particles from the solar wind coming into the Earth surface, respectively the Earth atmosphere, through the magnetic field lines of the Earth. And these magnetic field lines are pretty much vertical around the magnetic poles, north or south. That's why these particles come into the atmosphere. They never come in the atmosphere from in the equatorial regions, only from the poles. So this is going to be flying over the Indian Ocean, and on the right-hand side you will see southern lights, beautiful southern light. Here we go. This is a dream sequence. Look at that. You have the solar rays which are tracking the sun, although the sun is below the horizon, but they come in their proper position for sunrise. And you see the extreme dynamics of the southern lights due to this flux of particle from the solar wind. And the landscape illuminated by the moon. So we go toward the northeast now, and you see above the Earth horizon this layer of emission is called the air glow, surround the whole Earth, visible at night, but it's also present during the day. And look at this very interesting dynamics of the southern light. Pretty much like a dream. Spaceflight is dream. It's work, it's fun, but it's dream also. Very active aurora here. Southern light. And there was a satellite here moving from left to right. See the stars rising, and you see the stars also through this emission layer. You start to see some light close to the horizon. This is shortly before sunrise. Okay, a few words about the future and the so-called lessons learned. This is finally the title of this presentation. NASA has clear ambitions to go to Mars someday. I mean, they went to the moon in the 60s, then back to low Earth orbit to do a lot of work, and to build the International Space Station, to launch the Hubble Space Telescope, this Discovery machine, and do the maintenance. But someday, NASA and certainly other nations also want to go back to other celestial objects beyond the moon, and Mars is the target of choice. There are a lot of studies and pictures of Mars taken by various spacecraft. This is a picture of the surface of Mars taken by Mars Express. It's a satellite or space probe of the European Space Agency on orbit around the red planet, delivering such pictures that you see here. Very high-resolution pictures. This is not the Sahara Desert. You see some craters here. You don't have these in the desert here on Earth. It's Mars. And it's just to indicate the great precision of the pictures that we get from Mars from space probes on orbit around the red planet. Now you have had several generations of robots on Mars, all American robots. And the last one is Curiosity. And Professor Elachi, the director of the Jet Propulsion Laboratory, will be here tomorrow, and he will address, I think it's in the afternoon from 4 to 5. He will talk about space and Earth exploration, and he is the director of the institute that launched that Curiosity project, and is doing all of the commanding and getting the data out of Curiosity on the surface of Mars. So be sure not to miss this lecture tomorrow. It's going to be really, really interesting. I think that human spaceflight on one hand and the piloting of robots on the surface of other celestial bodies like Mars are the two great accomplishments of spaceflights of the past several decades. And this is certainly a really remarkable accomplishment. Landing a robot like this one on the surface of Mars after 8 months of travel with an accuracy of a few hundred meters is absolutely fantastic. We have other robots in the solar system. We have one called Cassini on orbit around the ringed planet Saturn, recording details of the surface. Here you have the shadow of the ring of Saturn and one of 60 satellites around Saturn. You have here an amazing picture. This is a conjunction of two satellites of Saturn. You have the rings and the shadow of the ring of Saturn on the surface of the planet. And Rhea is a big satellite here. Epimetheus is a small one. And this picture was taken when there was a conjunction of these two objects. And imagine the challenge of taking such a picture. Saturn is about 1 light hour away from us. If you want to command Cassini, the signal for the command will take 1 hour at the speed of light to go to Saturn. And of course the result you will get with a delay 1 hour also from the picture taking until you get the picture on the ground. Quite an accomplishment. Okay, the lessons from these a little more than 50 years of space exploration, I've tried to summarize them here. What we have learned, and we have learned this with work on Hubble and with work on the International Space Station and people staying for about 6 months on the ISS, human being can live and work efficiently up there. When Gagarin went on his single orbit of 108 minutes around the Earth in April 1961, there were fears that he would not survive. Now we know that not only we survive, but we can be efficient and we can live there for quite a long time. We adapt to this environment. Competition has been replaced by cooperation. There was the Cold War climate, very harsh Cold War climate at the beginning of the human space exploration, and now we work together on Hubble, we work together on the International Space Station, and cooperation has replaced competition, and many nations will join. The Chinese, India, Saudi Arabia, why not? In a few years from now we could cooperate in space. Enormous potential for science, especially astrophysics, whether it's using telescopes like Hubble or whether it's visiting a celestial body in the solar system using robots or space probes. We have learned a lot about the solar system. When you consider these last pictures of the satellites of Saturn, we know so much more about these than we knew before, thanks to space systems. And the last one is related to Apollo. It seemed impossible at the beginning of the 60s to go to the moon and bring people back alive before the end of the decade of the 60s, and it happened. And I summarize it by saying, if you really, really want it, you can do it. There was so much will by the US nation to accomplish that successfully that finally they made it. If you really, really want it, you can do it. Now I'd like to say a few words about what we are doing in Switzerland, especially at EPFL, where Stefan Katsikas was working for many years and where I am now teaching a course in space mission design and operations. I just show 3 slides of what we are doing at the Swiss Space Center, where we coordinate the space activities within Switzerland. We designed, fabricated, launched so-called Swiss Cube, which is a CubeSat. It's 10 centimeters by 10 centimeters by 10. It's 1 liter and has to weigh less than 1 kilogram. These are the specifications of the CubeSats. And we launched this one with an Indian launcher in 2009 with the idea of recording the air glow that I talked about before with a little camera. And this was a great tool for students to be involved in the design, construction, launch and operation of a small satellite. We are now in the process of being part of, not being the lead, but being part of another project called Cheops, which will have as an objective to record the existence of extrasolar planets or planets around other stars than the Sun by visually recording or recording the reduction in the light from a star when a planet comes in front of it on its orbit. Cheops. And a really interesting project that was launched at the end of last year is Clean Space One. There are a lot of dead satellites on orbit, and there are also upper stages of rocket that have no more function, but they are on orbit. And the risk of collision with real spacecrafts and active satellites is quite high. It happened in 2009 between a Russian satellite and an American satellite, communication satellite, and created a lot of extra debris. So in order to avoid the production of more debris in space by collision of big debris, the idea is within a few years from now to start removing the big debris. And the EPFL, and the Swiss Space Center in particular, together with other institutions in Switzerland, is launching a project where we're going to pick up SwissCube, the satellite that I talked about before. It is still alive, but in a few years it will no longer be, and the idea is to go and get it and deorbit it in a controlled manner. And for this we are designing a small satellite that will do automatic rendezvous with SwissCube. We'll grab it with a robotic system, and then the two of them will be deorbited, come down in the atmosphere in a destructive manner. We don't try to recover SwissCube. And this is a demonstrator for a technology to remove debris in space. This is a scenario of the mission liftoff. Then we have the chaser, which is our Clean Space One, finding SwissCube, grabbing it with a robotic system, and then the two of them will be deorbited in a controlled manner back in the atmosphere in a destructive manner. And my hope is that we can find some avenues for cooperation with KAUST in these projects, whether it's scientific satellites or whether we do the Clean Space One together. There is definitely room for cooperation. There are a lot of students, graduate students working on this project under the lead of a project lead person with experience. And I think there's certainly a possibility of cooperation with students and staff of KAUST in such a project. But we have to remember always, we go into space, we do really tough and interesting things in space, but we never have to forget that one of our primary responsibilities as human beings is and will remain to take care of planet Earth. And I know that KAUST is really in the middle of this with these faculties looking into water supply, energy, and preservation of the environment. We all work in the same direction, and I think cleaning up space goes in the same direction also, because if we don't do it, soon space will be inaccessible, and space is really essential in order to support these activities that have as a target to protect planet Earth. Thank you very much for your attention.
Claude, thank you very, very much for this extraordinary suite of adventures and beautiful pictures. I'm sure that our students, our staff would like to ask a few questions. I personally had no idea that we have started to put so much things into space that we have to start cleaning it, all right? Well, at least we can benefit from the fact that we're cleaning our environment, and we can take the lessons and bring it out of space. So are there questions? I hope there are some microphones in the room. I will not do that in this row, but there is a question over there, and then I will leave you the microphone and you look for the second one. All right?
Thank you. That was a riveting and remarkable address. I just wanted, as a fan of a certain genre of film, to ask a question about, was there ever a tiny, tiny part of you when you were working that was just scanning the horizon potentially for other craft or other vehicles from far, far away? And more seriously, as part
Yes,
of,
no, I think...
I mean, were you trained, were you given a protocol to, in the very, very unlikely event that you might...
Well, I must say that as astronauts, we keep our eyes open for anything that can happen. And I personally am a believer in the fact that there must be life everywhere in the universe. Even though we may think that the development of life on Earth, which led to human beings who are able to ask themselves questions about their origin, which is, in a way, in terms of development of life, something quite remarkable. I don't know whether the same happened elsewhere, but some forms of life, or many forms of life, must exist in the universe. And for me, I get its inspiration from the Hubble ultra-deep field. There is so much in this universe. Each galaxy that you see on this picture of a small window in the sky has about 100 billion stars. Many of these are accompanied by planets. And I cannot imagine that life developed only on this planet, planet Earth. So there must be a lot of life in many places in the universe. Of course, the distances are very large, so a visit from one planet to the other by spacecraft, whatever the level of advancement of civilization is going to be very difficult. But I would not exclude at all that we get visited, because we have just started human space exploration. We'll go much further away, and we may be visited faraway places someday. We saw a lot of things that we did not immediately understand, but eventually we had an understanding of everything we saw. So, and I can tell you very honestly, I did not see anything that I feel was like a UFO piloted by some green species monitoring us or monitoring humanity. No, I did not. But I know a lot of astronauts. We are a very friendly family, and I have had no statement by any astronaut that he or she saw something that was obviously a UFO coming from somewhere where there is life in our galaxy. So, but I had really, and I can tell you this very honestly, I had eyes quite open to be visited. We have not been visited. At least I didn't see anything.
First of all, thank you very much for your speech. And I have a kind of a silly question maybe. How likely is, in your opinion, that a person like me could go in space, maybe not for recreational purpose, but for parascientific purpose, or even just to be able to take a look at the Earth from there?
Okay. Well, if you want to be a professional astronaut doing work in space, whether it's International Space Station, you have to belong to a space agency, whether it's NASA or the Russian Space Agency or the Canadian Space Agency or the European Space Agency. And the limitation is that there are very few seats available. It's not the lack of talent and will to do it, but it's there are so few seats available. But the probability is never zero for anybody, but it's small mainly because there are so few positions available. For instance, in Europe we have 20 member states of ESA. Now we have 14 astronauts. So each nation does not even have its astronauts, men or women. Switzerland has had one. I was the one. I don't have any successor, not because we are lacking talent and will to become astronauts in Switzerland, but because there's no room. And as you know, you had Sultan Al Saud from Saudi Arabia, who flew on the shuttle once. So from Saudi Arabia, there was one astronaut. There will be certainly successors, but in small numbers because the seats are so few. Now, this is for the professional astronauts. Of course, now there is a rise of space tourism, and Richard Branson will offer, starting maybe next year or the year after, flights into space, but suborbital, go up and down from New Mexico for tourists for a price of $200,000, I believe, to go up and down. And that's a flight where you will not go on orbit around the Earth, but you go up and down, and for about 5 minutes you are going to have on top of the trajectory weightlessness. And then you re-enter the atmosphere, then it ends up with an approach and landing pretty much like the shuttle. So that's another way to become astronaut, but it has its limitation. Personally, I would recommend to save money over a few years and wait until we have orbital flight for tourists. Because the real wonderful flavor of space flight is when you go around the planet and you can stay for days or for weeks, and you can enjoy sunrises and sunsets and see the city lights during the night. And of course, during the short suborbital flight, you won't have that. But it's a step. I don't have any critics to this approach, but it has its limitation. I would wait until we have orbital space flight for everyone.
Okay. Well, first of all, I have to thank you for your amazing experience lecture. And my question is, which mission or which objective on space exploration do you think is the most important to be accomplished in the near future? Maybe another trip to the moon, or to conquer Mars, or I don't know, other planets?
I think there will always be the exploitation of low Earth orbit because there's so much to do in low Earth orbit. The International Space Station is a world-class laboratory to do experiments in the space environment, and there will always be some work done on low Earth orbits. Now, if we want to go beyond low Earth orbit, I talked about Apollo, I talked about plans of the US to go to Mars. I think there's a justification to bring people on Mars. Of course, the robots do a pretty good work. The problem with robots on Mars, and I'm sure that Professor Elachi will talk about this tomorrow, is the time it takes to send a command to a robot and to get the feedback. Typically of the order of 15 to 20 minutes for the light to go, respectively any radio signal to go from the Earth to the robot, and then the same time to come back. So you send a command to the robot, it takes 20 minutes to get there, then you get the feedback 40 minutes after you send the command. This makes the exploration of a nearby planet like Mars extremely slow. This is one reason why it would be good to have humans, maybe not on the surface of Mars, but maybe on satellites of Mars, to command robot with a delta T or delay time of only a second or two or less. This would make the exploration of such an interesting planet as Mars much more efficient. And of course, there's another aspect. Humans have this will to explore. You know, we don't send robots to the highest mountains, to Everest, or to the depth of the oceans. People go there. And this is very deep in us, this sense of exploring, of going physically where our technical capabilities allow us to go. That's another reason why we send people to Mars, because we want it as human beings. But for better understanding Mars and maybe finding clear signs of past life on Mars, sending people will be significantly more efficient than having robots.
I wouldn't be original to say thank you for such a stunning lecture, but my question was actually the one you have just answered. I would like you to comment on the necessity of space exploration, namely by humans rather than by automatic machines, robots. So as far as I understood from your answer, it's mostly because of signal travel time and the explorational aspect, but is there anything else which pushes human to Mars and beyond rather than these technological problems with robots?
Yeah, in a way I answered that already before. We have this efficiency because the delta T, or the delay in time, is very small with humans, so nearly negligible. And also the will, because it's in our nature to explore that we want to do this. I think that eventually we are always going to use a combination of human systems and robots. Even when we have people on the surface of Mars, I'm sure they will use some robots in order to do exploration in areas that could be dangerous. Of course, the thing is that when you have human beings, you try to avoid that they get injured or that they die. And this is very constraining, and to a certain degree it is very expensive also. And we are always going to have to make a decisions whether we send somewhere robots or people, and in some cases we'll send robots first like we do on Mars, and then we send people at a later stage. I think that the far away future of space exploration will have a combination of robots and humans. Of course, robots will become smarter and smarter. Now the humans have the advantage of being able to make decisions and use their judgment. The judgment of robot is questionable now, but in 100 years from now, maybe they will have artificial intelligence such that they will be able to make decisions and take the right decisions in order to achieve something in exploration. We'll never solve the problem with the delta T, but in terms of smartness and flexibility in operation, the robots will become better. So in 100 years from now, we'll decide in some place, are we going to send people or robots? Robots will be better. The gap between the two will become smaller and smaller. I'm talking about human space exploration versus robotic for now. For the faraway future, the situation may be different.
Hello, thank you for the great presentation. I wanted to have a question. Lots of money has been spent on space exploration and research related to that. Could you tell me, other than fulfilling the will for space, the human will for exploration and what we now know from the planet, have we gained any pragmatic knowledge from exploring space, from space itself?
Not so sure I understood that. Okay, so the practical aspects. I would say yes. Beyond, of course, the knowledge we acquire on celestial objects on the Earth and on ourselves, this is one thing. But practical application, I want to mention what is being done on the International Space Station now. There's a lot of work, which is not science, but it's not more technology development, to do water recycling. Because the idea is to prepare the human flights in the solar system to Mars and beyond. And of course, you don't have water when you are somewhere between the Earth and Mars. You have only the water that you took with yourself. And of course, if you try as much as possible to recover the water, to reuse the water that has been used typically to drink your own urine after a certain processing, obviously, you are definitely at advantage, so you don't have to take as much water from the departure of your travel. So I think that this is a set of technology that will be very useful on Earth, and I know that here there's a department that is working on water and the supply of water on Earth and recycling of water, and there's definitely very advanced technology being used on the International Space Station to recycle water, to recover the water from perspiration and urination, basically, in order to have nearly a closed-loop system for the use of water. That's certainly a development that will have a lot of useful applications on Earth, and maybe possible cooperation. I know that this is a department that is quite active here at CAST.
Thank you for your oh, sorry.
Go ahead.
20 years ago when I lived in the US, I had a friend that worked in the military, and she actually tracked this debris that was in space prior to the shuttle launches. And so I was really interested to see on your last slides exactly what EPFL are doing to help bring back some of the debris. How widespread is this research amongst the other space agencies? Are a lot of companies getting involved in this? Because 20 years ago, there was an incredible amount of debris, so I hate to think what amount of the debris is now. And I really think that this is going to be a huge problem.
Yeah, for the debris tracking and removal, it's certainly something that will require cooperation between nations. There's no doubt about that. In a way, this is the responsibility of the spacefaring nations to clean space. And it's also a responsibility of the spacefaring nations to develop a way to deflect asteroids that are threatening the Earth. There's no such threat for the following few years, I would say, but maybe in 20 years from now, 30, 50, we may see that there is an asteroid of large dimension that is going to hit Earth at some point. And there are such objects as so-called near-Earth object, NEO, that have orbit that are relatively close to the orbit of the Earth. And every now and then there is a crossing at an uncomfortable distance. And someday, I would not say there might be, but there will be, if we wait long enough, there will be a collision. And this could be devastating for life on Earth. And it's the responsibility of spacefaring nations in a cooperative manner to design a way to deflect or to deflect the asteroid or to prevent such a collision. That's one aspect of removing debris in space. I'm talking about a very big debris that is threatening life on Earth, over and beyond what I talked about before, which are debris on low Earth orbits, which threaten the lifetime of active satellites in space because of potential collisions. It's definitely a subject for international cooperation. NASA is working on it, the European Space Agency is, the Russians are working on it. We are trying to develop now the Clean Space One as a demonstrator, but we have a lot of support by the European Space Agency. It's a joint effort by many nations because it affects all of us.
So first I'd like to thank you for that great presentation with its breathtaking visuals. My question is, what do you think will be our future means of reaching low Earth orbit and beyond? Do you think we will keep using regular rockets as we do now? Do you think we may go back to reusable launchers such as the Space Shuttle? Or do you think some more ambitious projects such as the Space Elevator may have a chance to become someday a reality?
The classical rockets are lost once they have accomplished their mission. The Saturn V rockets for the Apollo program was totally lost to bring 2 people on the surface of the moon and then back to Earth. And the idea of the space shuttle was really to have a spaceship that is reused over and over again. It's mainly the cost of the engines. A rocket engine is very expensive piece of technology, and if you look at the space shuttle main engine, these hydrogen engines, they are very, very expensive. If we had lost them at every mission, it would have been really, really waste. So this was the idea originally that led to the space shuttle program development, manufacture, and operation, to reduce the cost of every kilogram brought to low Earth orbits by reusing mainly the noble elements like the engines. Unfortunately, what NASA didn't realize was that the maintenance between flights was significantly more extensive than had been anticipated. And instead of having some kind of an airliner, space airliner, we had a spacecraft that was reused, yes, but with a lot of maintenance in between, typically 6 months of maintenance and very costly repairs, exchange of tiles, exchange of turbopumps. So finally the cost was not so much an advantage. Right now, the cost of, or let's say a few years ago when we still had shuttle operated, the cost of every kilogram brought to orbit by the shuttle or expendable rocket was about the same or a little bit more costly with the shuttle. But again, this was an experiment. NASA had this noble idea of reducing the cost by having reusable technology, but it didn't work that way. At least now we know. Before we thought we had the solution, now we know that's not the solution. Finally, the Soyuz, the Russian Soyuz, is the least expensive way to bring people into space and back to Earth. It's a non-reusable technology, but it's very simple technology. It's very reliable. It's very cramped, it's not very comfortable. You don't have the luxury cockpit of an airliner, but you have cramped quarters. But this is probably, at least at this time, the better way to bring people to space and back, using simple technology and capsules like the Russians do now.
Thank you very much for your wonderful lecture. I have two questions. The first one is, what is the collaborative role of the various aerospace agencies? I mean, do they only, for example, share astronauts, or they give each other equipments and they are involved in certain projects? The second question is, in your point of view, which aerospace agency do you think is contributing better towards understanding space? Thank you.
Okay, well, the cooperation between sparing-faring nations that have activities in space is not only on the subject of exchanging astronauts or giving opportunities to astronauts of another nation to participate in missions of a nation like the United States, but it's really jointly deciding on what will be done and why and how. There's a board within the group of nations that exploit the International Space Station, and they jointly decide what utilization they will have as a space station, what will be the active space centers to control the activities, what will be the deadline for the supporting financially the operation of the space station, which right now happens to be 2020. They decide this jointly. You don't have one nation that unilaterally make decisions. It's jointly decided. What was the second question? Can you repeat? Oh, you don't have the microphone anymore. You remember?
I have the microphone actually, but we said the last question. But tell us what was the second question? Sorry. Is there a ranking between national space agencies, and is there a number one in your opinion?
Okay. Well, I would say that there is a lot of mutual respect. Each space agency has its strengths. There's no doubt that the US is quite dominant in the space activities now. They are the one that have the main control center for the International Space Station. The Apollo program put the US very high in the spacefaring nations without any doubt. And the Shuttle program was tough, and they successfully made these 135 missions, minus unfortunately 2 accidents. But the Russians are very respected also because they have taken this other avenue with consistently improving but very small improvement of the Soyuz system, so that now they have a very reliable, although somewhat old-fashioned space transportation system. So I can see a lot of respect between the Russians and the Americans because of the different development they took, and it's just different in ethics and in the way of doing things. Other agencies like the Japanese and the Canadian, the European Space Agency have quite a lot of achievement, but they don't have their own access to space for manned systems. We only have the Russians able to do this, the Americans, and of course independently we have the Chinese. There has been so far no cooperation with the Chinese on human spaceflight, although there has been little cooperation on automatic and satellite technologies. And then another rising nation is India right now, which has mainly the use of space for the profit of the Indians, Earth observation and communication. And they will maybe start human spaceflight in the near future, but no firm decision on that. To answer your question, there are some agencies that are dominant, and the US and Russian definitely are dominant. ESA is in quite a good position and is joining the forces of now 20 member states. Canadian, Japanese are quite good position also, and you have rising China and India. And cooperation is really the word of the game now, as opposed to competition at the beginning of the space exploration.
Professor, do you have time for just one more question, please, here? We met earlier today in my physics class when you came to speak to the Year 11 and 12 students, and I just wanted to thank you again so much for coming and saying the words you did. You showed us the Hubble Deep Field photo tonight again, and that's a photo that I think is one of the most important photos that's ever been taken. I've always showed that to my physics students to try and show them an idea of how big the universe really is that we inhabit. And it's such an honor to meet the man one of the people who made that photograph possible.
Well, thank you very much. Yeah, the Hubble Deep Field is also, I would say, the picture taken by Hubble which touches me the most. The idea of leaving a telescope pointed to the same small window in the sky for 10 days and collecting photons for such a long time to record the most distant object visible has an incredible nobility, I would say. And what we have learned from the deep field is incredible.
What it does for us on Earth, I mean, we haven't had the chance to go into space, but it gives us an opportunity to maybe have our minds opened in some special way to the size of the universe. You've had the experience of being able to look down on Earth, the whole thing. And that's something most of us can only dream of, and what that might do to your perspective on life and history and the purpose of a life on Earth and our role to play to serve that. Could you speak for just one moment, please? Is there something that you brought back down with you, a perspective that transcends?
Well, I think that human spaceflight also has had a lot of positive influence on me, in the sense that I learned to work within a system that has a lot of mutual respect. I remember the mutual respect within crew members on the same flight, the respects between the personnel in the control room, the flight director, and the lead of the flight director and the crew, the respect we had for our instructors. It's a world which, from a human point of view, is extraordinarily rich and positive. And this was, for me, beyond the possibility of going to space and having these incredible views of the Earth, and doing work with a power tool, spacewalking, which was great, but at the same time tough. You know, they're always the two things. The human aspect of my experience as an astronaut has been absolutely wonderful. Mutual respect between people, I think, is one of the most important ingredients for success in such an endeavor.
So this time I will keep the microphone, so it will be the last question. We have a student in bioinformatics, but she is not willing to ask the question herself, so she's asking me to help a little bit. Is that all right? So the question, if I understand it properly, but if I don't ask the right question, then you have to correct me with the microphone. All right? So the question is whether the work that is being done in space is leading to potential new sources of energy that we could use on Earth. Is that correct?
Okay, well, that's an interesting question. I would say probably not. For me, the main source of energy for the future of humanity is definitely the sun. The sun gives us such an enormous quantity of energy on the Earth. We just have to collect it. And of course, a country like this one has pretty good weather conditions. So I think in the future, when we go beyond the peak of oil, which already has passed, but it's in 40, 50 years from now, when oil will be more difficult to get, tapping the energy, the radiation energy of the sun, and making electricity out of it, or producing hydrogen and oxygen using fuel cells to produce electrical power.
So there is
These
no
are
more-
certainly good sources for the future. Now, as far as new energy sources found in space, I would say no. Although
what
we
about-
made this interesting experiment with a tether conducting
What about the helium?
big-
Helium? The helium?
helium. Not really. I mean, I know some people think that helium-3 on the moon could be a potential source of energy. This is very disputed. And we have to realize that if we find a substance on another celestial body that would be useful for generating energy on Earth, we need to go and get that material from that other celestial body. And we have to consider the cost of it and the complexity and maybe the danger of it, although if it's done with a robotic system, there's no danger for humans. But we always have to weigh the potential of getting something out of somewhere and the cost of bringing it to Earth. I think that one possibility is the mining of asteroids for raw materials, for lithium, for instance. With the rate at which we build lithium-ion batteries, we will deplete the lithium on Earth relatively rapidly, and we may have to go to other celestial bodies to extract lithium and other substances. I don't believe too much in helium-3, but in the faraway future, in a few decades from now, going to asteroids to get other material that are essential on Earth, I believe in it. The advantage of this would also be that mining is normally a relatively dirty activity for planet Earth and for the atmosphere. If you mine an asteroid, you don't pollute the atmosphere of the Earth, so that would be an advantage.
Claude, thank you very much on behalf of everyone. I think that Professor Susana Nunez would like to give you a present on behalf of KAUST and what?